do that.
Okay, today's video is about graphing absolute value functions. So by the end of the view, from the way we're going to do it, we're going to apply the graph transformations we did in the last video. Remove graphs left, right, up, down, flip them upside down if we needed to, and use that to graph any absolute value functions. In order to do that, we need to figure out where or what the shape of absolute value functions are, where they come from. So right now, I have graphed just plain old y equals x. So when x is 0, y is 0. When x is 1, y is 1. When x is -5, y is -5. And we need to think about what an absolute value does to numbers. So the absolute value tells you the distance from 0, which in effect, positive numbers just leaves alone. 3 is 3 places from 0. 5 is 5 places from 0. But on the negatives, -1 is 1 place from 0. So this -1 becomes a positive 1. And it'll go there where point A is now labeled. -2, absolute value, is +2. So instead of down here where that line continues, it would be there where B now is. We can continue this a couple more points. So -3, absolute value is +3. -4 is absolute value is +4. So all the points on this side of the line, the positives, are just fine where they are. But the points down here in this part, instead of going down here into the quadrant 3 of the graph and the negatives, needs to come up here in quadrant 2 and the positives. So what you get for absolute value of x is this classic V shape. Okay, now all absolute value graphs are somehow based off of this V. If you start with something other than just a plain x, like if you start with an x squared, you can get weird W's and things. But we're just going to do the absolute values of lines. So you're going to get a V, and this is y. Everything on the whatever line you were looking at that was negative now flips over and becomes positive. Alright, so let's look at the examples. I have them listed over here. G of x, absolute value of x minus 3. Notice where this -3 is. It's inside the absolute value with x. As we talked about last video, adding or subtracting something in with x moves the graph left and right. A -3, because of the way the negatives work, actually moves it 3 to the right. So if you were to take every point, move it 3 to the right, you get the exact same V shape just over here. That's why that V is there. Notice the slopes. Up 1, over 1, up 1, over 1. Because the V, it's up 1, over 1 in the other direction also. Up 1, over 1. So we have the slope of 1. This side's actually -1 because of the way the thing flipped. And it's just this exact same parent function just moved over. Compare that with the next one, h, which is in kind of a hot pink, absolute value of x, and then a +3 tacked onto the end. Like we talked about yesterday, when you add something just tacked onto the very end, that shifts the graph up or down. So +3 would be up 3. So this corner of the V, which we call the vertex, is going to be moved up 3, 1, 2, 3, and it'll go right there. The slope will still be the same, up 1 and over 1 both directions. And there it is. And go to the other one. Exact same V shape, moved up 3 places. Every point moved up 3 places. The next example just combines the previous two. We have that move of 3 to the right and 3 up. You can kind of see it superimposed over the absolute value, the original absolute value graph. Vertex has been moved 3 to the right, 3 up. We still have that same slope of 1 and -1. So we're going up 1 and over 1 both directions. And there you go, applying that. The other type of transformation we talked about when we were doing those graphs the other day, in the last video, was if you put a negative out front. That reflected the graph, flipped it upside down, over the x-axis, so it'll be opening down in this next case. We also have a move of 2 to the right on this. So the vertex is going to move 2 to the right, and instead of opening up, it's going to open down below the x-axis, like so. Notice the slopes are still there. We're just going down 1 over 1, down 1 over 1, down 1 over 1 to get us that shape. So you see, once you understand what the shape is of this parent function with this slope of 1 both directions, then you can get all these other graphs just by moving all the points left, right, up, down, flip it upside down, whatever you need to, based off the individual problem. Now, the next example, R. The thing that's different now is this 1/2 in front. 1/2 absolute value of 2 plus, or x plus 2 minus 4. Well, the plus 2 inside we know how to deal with. It's going to be a move of 2 to the left. The minus 4 we know how to deal with. That's going to be moving everything 4 down. But what about this half? Well, that's your slope. So instead of going with the slope of up 1 over 1, we're going to go up 1 over 2 in both directions. So let's see what that looks like. There it is. Notice vertex has been moved 2 to the left, 4 down, and now the slope is up 1 over 1, 2. Up 1 over 2. Up 1 over 2. Up 1 over 2. And so forth. And the same on the other direction, because we still need to keep that same V shape. Alright, so let's look at S, the next to last example. We still have just a shift of 2 places to the left, so the vertex is going to be right here at -2, 0, because there's nothing added on the end. The negative means we're going to open down. And this time we have a slope of 1/3. So we're going to go down 1 over 3. So it should go through this point over here if you count it. Oop, wait, no, I'm sorry. Start at -2, sorry. Start there. Down 1, 1, 2, 3. We should go through the point 1, -1. So if I'm starting to get confused, the baby is crying in the background. So, must be feeding time. Anyway, there it is. Vertex, as we said, has been shifted to the left, has not been moved up or down at all. The negative makes it open down, and the slope down 1 over 3, both directions to get that V shape. So finally, what are we going to look at for this last one? This last problem is a little bit trickier. I need to, oops, I probably needed a place to jot this note down. I don't really want to get out my tablet just for this. Notice the problem is, inside the absolute value, we don't have a plain x plus or minus something. We have a 2x. So we need to factor that out. Let me see here. Can I do this? There we go. We need to factor out that 2 because we need just a plain x inside the absolute value. So we can, oh, that's awesome. We pull the 2 out of the absolute value. That leaves us with an x. Minus, we got to take the 2 out of both things inside that absolute value. 6 divided by 2 is 3. And then the plus 1 at the end didn't have anything done with it. It's just tacked on to the very end. So we're going to start at 3, 1, because we're going to move the vertex 3 to the right, 1 up. So we'll be right over here. And then the slope is going to be 2. So up 2 and over 1 both directions. Like so. Moved from 0, 0 to 3, 1. Slope of 2, so we went up 2 and over 1. Up 2 and over 1 that way. Get that nice V shape. Notice it is much steeper than it was for the original parent because the slope has changed. This has a slope of 2. This only had a slope of 1. So that pretty much does it. The assignment has a handful of graphs from 2 of the different pages in the book. It's just doing these absolute value graphs. There might be a couple lines in there just to make sure you're staying awake and paying attention. So watch out for just regular lines also in there, mixed in with the absolute values. Apply that V shape. Apply the transformations we did the other day. And it shouldn't be that big of an issue. And then we'll work on that in class tomorrow. Okay? Thank you.